So as Dr. H.K. said, I'm presenting on the topic of integrating theoretical and empirical measures of ecological stability. Are they measuring the same thing? My mentor was Craig Jackson, and I've also worked with Dr. Amy Downing and Shannon Schlater. So what we're looking at is a particular food web. We have these herbivores here. These are different types of zooplankton, and we have the algae that they eat. We have population data on these of varying compositions, so we end up with like different sections of this bigger food web, so little food webs. So one composition might be just Daphnia, another composition might have just these three, so on like that. And we have this population data from other mesocosm experiments that Dr. Downing has completed over the past summers, where she had many, many tanks of these different compositions, and so there are many replicates of each composition. And then when we look at the population data, we see like lots of different fluctuations between the population levels from collection points. And here we have the tank that has, we have one tank that has just Daphnia and Scapholibris, and we see here's our algae line, it goes down pretty quick, and we have one species that fluctuates a lot here, and one that fluctuates lower. Here, when we have all 4 different types of species, we have, again, the algae goes down low, and we have other species fluctuating higher, a lot more fluctuations and variability. So we look at this and we see that there are different patterns of variability, and from that we're trying to understand which is more stable, how do you compare different levels of stability, and what does that mean and what influences stability. One of the things that ecologists are expecting will influence stability are the presence of weak interactions between species. Well, if you have 2 species, say Daphnia and Scapholibris, they could, negatively impact each other, positively impact each other, and do so in a stronger, weak way, have a stronger, weak effect on each other. So we also investigate if we have more species that are weakly interacting, if that leads to a more stable system. So our big questions are theoretical measures of stability related to empirical measures of stability? And also, are systems that have more weak interactions more stable? To answer these questions, we need to define empirical measures of stability and theoretical measures. For the empirical measures of stability, we use a coefficient of variation, which is just the standard deviation divided by the mean. It's a normalized number. So we can do that either for a population, where we just use the population biomass data, or we could do that for the entire community, where at each time step you add all of the biomasses together. And if we want to choose just one number for a particular composition, we would be taking either the average or the weighted average of the population coefficient of variation, if we're interested in that. Now, to get our theoretical measures of stability, these are based on what's called a community matrix that contains the interaction strengths between all the species. And to obtain that, we have to use a modeling process called MAR1, which is the first order multivariate autoregressive model. So what this does is takes log transformed population time series data and also log transformed covariate data, which might be, in our case, the levels of nutrients that are added to the tanks or the presence or absence of predators. And then taking that data, it fits the community matrix and also a matrix that tells you the different effects of the covariates, as well as an A vector related to the mean, so that we can predict that based on the values of the populations at time t, what will be the populations at time t plus 1. We also have this noise vector, so that's white noise vector representing environmental fluctuations that give this a more realistic view of nature. So then we find this A vector related to the mean, the B matrix, the community matrix, and the C matrix for covariates for each tank, and then we average over all the replicates to get our B matrix for each composition. So based on this, we have our theoretical measures of stability. Our first is asymptotic resilience. It is the rate of return to equilibrium. And so R infinity equals negative log of the magnitude of the dominant eigenvalue of B. And so it is stable if R infinity is greater than 0, which will be the case for each of these compositions. We also have initial resilience, which is the opposite of the maximum initial growth of a perturbation. So we can look at that simplified down to negative log of the spectral norm of B. And we have a reactive system if R naught is less than 0. So a system that is more reactive is seen as less stable. Further, we have intrinsic stochastic invariability, which is the inverse of the maximum variation in population data due to white noise. So we have two covariance matrices for our data. The first is the population covariance matrix, which is V infinity, and we also have one for the environmental noise, which is sigma, and we also have this equation that relates them. Now, if we generate data or simulate data, we can force it with all different types of sigma. So we want to see what's the largest size of V infinity when you force it with using different sigmas that all have the same size of Frobenius norm of 1. And so the larger size of that is the intrinsic stochastic variability. And so we use the inverse of that here. Now for the results, we have empirical and theoretical stability. In this case, we did not find any significant correlations. We have the p-values here, and the lowest one is 0.142. So this leads us to conclude that there's not evidence here for any relationship between these two different types of measures of stability. However, we can go look at empirical stability and interaction strength. So we have different measures of interaction strength on the bottom, since ecologists think that it might be the overall interaction strength, there might be particular interaction strengths that make a difference. And then measures of CV empirical stability over here. And we have two significant correlations here. We have this light gray one because the probability is less than 0.05. And then we have this one here for the probability is less than 0.01, darker gray. So of the 21 comparisons here, we had two significant correlations. And then finally, comparing theoretical stability and interaction strength. Again, we have measures of interaction strength on the bottom, and then we have theoretical stability on this axis. We have 13 significant correlations of the 21, one of which is very significant, so p is less than 0.01. And so this is exciting. In most cases, we have a negative relationship, so as interaction strength increases, stability decreases. Though we do see for mean top-down edible interaction strength this positive relationship. Lower interaction strengths of this particular type are destabilizing, even though we only see one that's significant here. So that's interesting for a future study. So conclusions. There's a clear link between interaction strength and theoretical stability, as well as a weaker link between interaction strength and empirical stability, though there is no evidence of a connection between empirical measures of stability and the theoretical measures. So future work, we want to look at what does the simulated data say about these different comparisons, as well as is there an effect of species richness on stability or interaction strength? And then finally, we want to learn more about how do the systems themselves contribute to weak interactions? What are those particular characteristics that make these possible? So, thank you.
Thank you, Claire. Questions, comments?
Yes.
Can you go to the slide that has about 20 or 21 scatter plots on it?
This one?
Either one.
Okay,
Yeah.
this one.
Sure. If I were to take a look at two adjacent scatter plots, are the tests that we're doing there correlated with each other? Or are these independent tests that are being run?
These data points are based on real data. So across this entire line here, we have the same values of asymptotic resilience for each particular composition. Does that answer your question?
So what's the difference? Look at the upper left-hand two plots.
Yes.
Yeah. What is the x-axis on each of them? I can't see it because my
Oh, sorry, yes.
middle variation.
We have mean interaction strength here and mean off-diagonal interaction strength here. So the mean off-diagonal interaction strength but does not use the interactions of the species on themselves.
So you're running essentially 20 significance tests, each at the 5% level of significance, right?
Yes.
So there's like a 5% chance of making a type 1 error every time you do this, right?
Mhm.
So the slide before, I think it's interesting, and I'm trying to wonder if there's anything meaningful here. I mean, it's interesting that you have 2 flagged results
Yes.
out of 20, which is kind of what you would expect if there was absolutely nothing going on. I'm just pointing out that if you were running 20 independent significance tests 20 different times, 5% of the time you would falsely reject, just from random chance.
Yes.
Do you think anything like that might be going on here? That's why I asked about what's the relationship between one plot and another plot?
Okay.
Are they truly independent, things that you're testing, or not? I'm trying to get a handle on that. I'm not trying to be difficult, or
Yes. No, I understand. Good questions. Here, this has p equal 0.005. So my interpretation is that's less likely to have this accidentally.
sure. Okay.
Other questions?
Yes.
Just a really basic question. If you go back to the equation, the slide with like the temporal equation on it.
This one?
Yeah, what's U of T? I missed that.
Those are the covariate levels. So the nutrient levels that we put in or the presence and absence of predators.
So it's okay. So it's like how much?
Some tanks
it's,
had,
it's a measure of the environment.
yes.
Okay.
Some tanks had fluctuating nutrients, some had nutrient levels that would just have to be added to keep the system stable.
Okay. Got it.
I have a sort of piggyback question on that. When you say
Yes.
predator, you're talking about not the zooplankton that you put in on the algae, but say like the snails or something that would eat the zooplankton, right?
Yes, something that would eat the zooplankton.
Is the large plankton just grown-up plankton, or is it an algae, or is it a different variety of algae?
They are zooplankton.
It's a plant, so it just grows, right?
So these are kind of animals. These are animals, and these are phytoplankton, which are more like plants.
I know,
Oh, but-
but
Okay.
the larger
Oh,
ones,
the large
are they just
ones.
grown-up versions of the smaller ones, or,
They're different species, and the way that they grow makes them edible or inedible.
okay.
And Claire, could you remind me of the definition of the dominant eigenvalue?
It's the eigenvalue of a matrix that has the largest absolute value.
Any other questions? All right, let's thank Claire again.